All right, guys, last time we talked about how to determine the equation of a sinusoidal function or a trigonometric curve. And today we're going to go over an application word problem from the Grade 11 Ontario textbook. So the difference between this problem and what we went over last time is that last time at least you're given a curve, right? It looks something like this or whatever, depending on the situation. And this time you're given nothing but words. So essentially, right, if what we did last time was called model fitting, given a graph, now this time you simply need to add one more step, which is actually graphing it. What kind of behavior do you need to model? So let's go over this question together. The question reads, Milton is floating in an inner tube in a wave pool. He is 1.5 meters from the bottom of the pool when he is at the trough of the wave. A stopwatch starts timing at this point. So that means when t is equal to 0, he's at the trough, and that is 1.5 meters from the bottom. In 1.25 seconds, he's on the crest of the wave, or the peak, 2.1 meters from the bottom of the pool. Part A asks, determine the equation of the function that expresses Milton's distance from the bottom of the pool in terms of time. So let's try to graph this first. So let's draw a Cartesian plane. Your x-axis represents time, and it must be measured in seconds. It's crucially important that you label the axes correctly. And your y is measuring the distance from bottom of the pool, right? And that is measured in meters. Okay, so let's see what's given to us from the description. Okay, he says when time is equal to 0, so when the stopwatch started, he was at the trough, right? And the question says that is 1.5 meters from the bottom. And at the trough of a sinusoidal function, it goes up like something like this, right? And eventually he's going to hit the peak, right? And the peak is reached 1.25 seconds after the stopwatch started, right? And the peak value he reached was 2.1 meters from the bottom. And of course, because it's a wave, it's a sinusoidal kind of behavior, and it's just going to keep going like this, right? Okay, so that's all we're given. This is actually enough to graph it. Remember, the general formula for a sinusoidal function goes something like this. Y is equal to a value times sine or cosine, depending on what kind of function you want to fit, of k times x minus d plus c. And you have four parameters, right? A value, k value, d value, and c value, right? And of course, right, some of the parameters they're gonna depend on whether you want to fit this to a sine or cosine. So let's make that decision right now. You're starting at the bottom, right, at the trough, right? So do you think it's easier if you fit this to a sine or a cosine graph? Well, actually, it's a lot easier if you fit this to a negative cosine graph. Remember, a negative cosine starts at the bottom because a positive cosine starts at the peak, right? So a negative cosine x starts at the bottom and goes right up, and then, right, it goes back down, right? So that's probably the easiest option because then your horizontal shift, so this d value, is going to be 0 because you don't have to do any horizontal shift, right? So that's one option. So let's try to fit this using a negative cosine graph first. So we determined that, okay, it's going to be a cosine. So let's erase the sine. And we know that because we want to fit a negative cosine, this a value, it must be negative, right? So what is the k value? Because that's usually the hardest to determine, right? We know that from the trough to the peak, right, the 1.25 seconds, that represents half a period. Half a period is 1.25 seconds. So you have to think about, okay, then what's a full period? Simply 1.25 times 2, right? Which is 2.5 seconds. Remember that there's a relationship between the original period of the cosine function or sine function, because they're both 2 pi or 360 degrees, right? and between that and the new period, which is the 2.5 seconds. So we know that the full period, 2.5 seconds, is equal to 360 or 2 pi radians over k, right? So that means k must be 2 pi over 2.5, right? So only when k is equal to this value can you convert 2 pi radians to 2.5 seconds. And let's simplify this a bit. So it's approximately 4 over 5 pi, right? If you want to see the full steps, sure. This is essentially 20 pi over 25, and that simplifies down to 4 over 5 pi, okay? So now we know the k value. So we have cosine of 4 over 5 pi. Remember, there's no need for horizontal shift. So we can put in a 0, right? Which is just x, right? So x minus 0. Okay, and we know that the a value must be negative. But we cannot determine the a value yet because we need to first determine the c value. So remember, c value is the axis of the equation. It's this middle axis that cuts through the wave, right? So if the peak is at 2.1, the trough is at 1.5, that means c value must be halfway between the peak and the trough, right? So the trough is 1.5, peak is 2.1, take the halfway in between, the midpoint between the two, and that is equal to 1.8, right? So I know that my c value is 1.8. If this value is 1.8, then we know the amplitude, right, which is your a value. So that must be 0.3. Are we done yet? Well, no. Remember, we said we're fitting the negative cosine graph so we can start at the bottom, right? If you just leave it like this, you're going to start at the peak. So we have to make sure this is negative. So that's our equation. Distance, right, as a function of time, which is t, right? So is equal to negative 0.3 cosine 4 over 5 pi t plus 1.8. Okay, is there any other equation? Sure. I know some people are going to try to fit this to a sine graph. Okay, if you're going to find this to a sine graph, remember, a sine graph starts at the middle, right? Then it goes up, and then back down, then to the trough, and back up, right? So if you want to fit a sine graph, you're going to have to start like right here and go up and then down and back up, right? So you're going to fit something like this. Okay, then that means you can keep the a value or the amplitude positive, but you're going to have to add a horizontal shift. Okay, so let's try to fit that. So if you want to fit a sine graph, so we know that y is equal to the amplitude, the absolute value of the amplitude doesn't change. It's always like you're increasing the amplitude by like the degree of, or you're increasing how much you want to go up is always 0.3, right? 0.3 meters. So that part doesn't change in this positive value, right? Sine, the horizontal stretch never changes. Right, because you're always your period doesn't change, right? It's still 2.5 seconds for a full cycle. And here's where it gets interesting. What's your horizontal shift? Okay, remember this value is a quarter of a period, right? And this is also a quarter of a period, right? It's not really drawn to scale, but you can see that, right? Because from the peak to trough, that distance is half a period, so that means halfway in between must be a quarter of a period. So we know that, okay, we know that the full period is 2.5, right? It's a full period. If I want to take a quarter of a period, so that's 2.5 over 4. And that is definitely not a very nice number, but let's just keep it that way, right? So that's equal to t, remember you're shifting to the right, so you're subtracting 2.5 over 4, right? And of course, your vertical shift, 1.8, never changes. And these two graphs, right? These two models are essentially equivalent. And for more details, you can look at the previous video when I fitted like various cosine and sine graphs, right? So you can have any of the two models, or probably there are more than two. There are more than two models, definitely, but any of the two models would be fine. Okay, so that's the first part A. Then part B, right? Part B essentially is saying what's the amplitude? What does it represent? It looks basically how tall is the wave from like the midpoint, right? So the amplitude is clearly 0.3. Meters, right? If you want to give it a unit of measure, and it represents how tall the wave goes from like its the axis of the equation. How far above the bottom of the pool is Milton at t is equal to 4? Well, that you can simply take any of the two equations in part C, right? Let's say I take the first one. You simply plug in t is equal to 4, right? So 4 over 5 pi times 4, right? You just plug this in. That's an excess bracket, so plus 1.8, right? So that's part C. Part D. If data are only collected for 40 seconds, how many complete cycles of the sinusoidal function will there be? Okay. Remember, one full cycle is 2.5, right? So if you collect it for 40 seconds, that means you can take 40 divided by 2.5, and that's how many cycles. Okay? Then part E is like, what if the period of the function changes to 3 seconds, right? What is the equation of this new function? Okay, so let's try that on our existing functions or equations. So I'm just going to keep the first one because it's going to be the same change for a second. Remember, the horizontal stretch factor, or the k value, it doesn't change whether you want to fit this to a sine or cosine. Okay, remember that relationship. The new period, right, is equal to the original period, which is 2 pi, or 360 degrees, over k, right? So if I want to change the period to 3 seconds, that means I have to set k such that 3 is equal to 2 pi over k. And that means k is equal to 2 pi over 3. That's part E. And that concludes this question.